and welcome to Military and Aerospace Electronics Tech Summit, quick chat with Coherent Logix, a processor and design tools specialist in Austin, Texas. I'm John Keller, Chief Editor of Military and Aerospace Electronics. Today's presenter is Doug Smith, Vice President of Sales at Coherent Logix. So thanks for joining me today, Doug. I understand you're going to tell us about HyperX family of processors and how these devices can provide design alternatives to traditional ASICs or FPGAs. So say I'm designing a new project and I want to know more about HyperX. What is HyperX and how is it different from other processors?
Sure, John, and thanks for having me. HyperX is the most versatile, massively parallel, software-defined processor in the world. HyperX is a completely new architecture that's 100% software-defined. By giving designers software control over their hardware architecture means that the performance of the system greatly depends on how and where software designers decide to use the HyperX hardware resources. It also means that the IP is truly reusable, not only on that version of HyperX, but on all versions of HyperX. This type of unprecedented software-defined architecture greatly reduces the cost and time to market while enhancing the performance and power efficiency, which lowers total system cost.
So the project that might be being designed, say one that typically uses a high-performance ASIC, general purpose processor, system on chip, or an FPGA. How does HyperX compare with these other core silicon solutions?
Sure. So HyperX addresses the shortcoming of existing solutions. Some of the shortcomings include performance to watt, flexibility to adapt to evolving standards, scalability issues for increasing computing performance, including upgrading I/O requirements. And customers are also concerned with development time, and our tools are available and easy to use. A big concern for executives is future-proofing, which is the ability to upgrade to future designs with previously developed code and IP. And lastly, the initial investment in unit cost. But before I close on that question, let me also just take a moment to talk about the three most popular choices in our industry, which are ASICs, FPGAs, and SoCs. ASICs are a popular choice and have the best performance and power efficiency, along with low unit cost. But ASICs have zero flexibility, zero scalability, with long and expensive development times. Development costs can reach $20 million or more, and development times are commonly 36 months. ASICs are best for applications that can afford a lengthy development time, plus a large capital investments. Moving on to FPGAs, and we'll save SoCs for last, FPGAs are another popular choice, and they have moderate levels of flexibility, scalability, and reusable IP. However, FPGAs consume far too much power, and high-end FPGAs are extremely expensive, and the development time takes 3 times longer when compared to an HyperX. This not only increases the overall cost, but there's some lost opportunity cost that needs to be a factor. And lastly, SoCs. SoCs are system on a chip. They do have good performance to power efficiency and low unit cost, but they greatly lack scalability and flexibility. All processor companies tend to advertise code reuse. However, it's typical for software engineers to discover when the SoC is upgraded that very little of the original code can actually be reused. And typically, they have to start from almost scratch. So HyperX is an excellent alternative for computationally intensive applications where efficiency, time to market, cost are key factors. And from a performance standpoint, HyperX delivers near ASIC level performances with the flexibility and scalability of lower cost of other solutions. Let me give you a couple examples. We'll just start with our rad hard space qualified HX40416. This guy has 416 parallel processors in a single IC. We call them, they could be called DSPs, but we call them processing elements because they do more than just the function of the DSP because they're integrated into our memory network fabric. These processing elements are embedded into a network of digital memory routers. These DMRs on our 40416 are capable of moving in total about 4.85 terabits of data per second into and out of the IC. That means interfacing to external sensors like multiple cameras, analog to digital converters, DACs, external memory, and/or other HyperX processors is done gluelessly and without any bottlenecks. It does this with the best-in-class power efficiencies by intelligently moving data within the system as needed and while powering down all unused computational units on a cycle-by-cycle basis. And by the nature of the architecture, has deterministic timing for all processes and applications. The nature of this architecture helps to simplify developer code while improving performance for time-critical applications. That's a long answer to your question, but I hope that I got it right there.
I'm sure you probably did. So, I'm thinking about HyperX and all the things that it can do. Well, there's all kinds of solutions available. And I'm thinking that HyperX probably can't be a fit for everything. Where is HyperX really the best fit? Can you outline, a couple of different design scenarios where it would be a good fit and, really help us enlighten us about where it might not be a fit?
Sure, great question, John. So HyperX processors are best suited for computationally intensive applications that are software defined and require power efficiency, flexibility, scalability, and relatively low cost. I like to use the term versatility to encompass all these features into a single word. Typical applications include edge computing for real-time communications and/or video imaging processing. HyperX is an enabling technology, and creative customers are finding new applications all the time. We have successfully deployed HyperX in a variety of image processing applications, and we've also used HyperX for software-defined radios. Those are just two of the examples. In a software-defined radio, only a high-speed A to D converter and a DAC, along with one HyperX, were needed to complete the entire software-defined radio. This single HyperX replaced all of the other components typically used and needed to create an SDR. Another great use case is where standards are continually changing, like ASTC 3.0, or more commonly known as Next-Gen TV. The changing standards make ASIC design nearly impossible and super expensive. HyperX delivers near ASIC level performances, plus it has an architecture that can be physically modified through software. The HyperX provides a flexibility wherever standards are changing. HyperX also has more versatility and flexibility than any of our competitors. Unlike graphic processing units, tensor processing units, or other configurable accelerators, the HyperX can implement any operation. For example, in many cases, neural network post-processing cannot be done on a graphic processing unit or a tensor processing unit. It is performed on an associated processing unit, which increases the total cost and power of the solution. These two-chip solutions also increase the overhead of data movement and adds to the end-to-end processing latency. Another example is receiving source data from a sensor. HyperX can receive data from various sources directly into the processing fabric, thus avoiding moving data from the peripheral bus to the main central processing memory, and from there to the appropriate hardware accelerator. Competing hardware accelerator often don't allow running more than one thing at a time. For example, if one needs to run two different neural networks on a graphic processing unit or a tensor processing unit in parallel, This will need to be serialized, whereas on a HyperX processor, there could be two neural network engines working in parallel. One set of processing elements is dedicated to the neural network engine, and the other set of processing elements to another neural network engine. And lastly, something we haven't even mentioned yet is the security features of the HyperX. HyperX comes with 256-bit AES encryption and physically unclonable function puff, which is built into the chip hardware to convert an encryption key into an activation code. And that's unique to that specific chip. Another area we're exploring is the security barriers within the chip that can be programmed to physically isolate sensitive sections of the architecture. So where would I recommend considering HyperX? Any of the applications that you may have that require two or more of the features that we've previously discussed.
All right. Now, a software-defined architecture sounds complicated and maybe it's difficult to program. Do you have tools that are available for developers that might help get them started and speed up the job?
Oh, we sure do, John. So HyperX hardware is programmed using an industry standard C or Python on our Eclipse-based ISD tool. Software engineers are able to meet product requirements using 100% programmable software-defined functions. These software-defined functions exploit powerful forms of pipelining and parallel processing. Coherent Logix licenses a vast library of software-defined functions for edge computing, software-defined radios, computer vision, and machine learning. Our HX ISD includes several things. Let me just run through the quick list of them, which is a C development environment, communication to other APIs, cross-compiler tool chains, cycle accurate simulator, source level debugger, real-time control and analysis, and managed build environment, all of this running on our Eclipse-based GUI. Yeah, so if you're interested in learning more, and I hope that you are, I hope to hear from you. And hey, John, thanks for the opportunity to share a little bit about our solutions.
Sure. I don't know if this is a dumb question or an irrelevant question. And if it is, just let me know that it's, doesn't have any bearing. But I'm curious about, now we talked about ASICs, we talked about FPGAs, general purpose processors. Does HyperX, is it also an alternative for the possible use of a general purpose, a graphics processing unit or GPU? Does the HyperX, have any bearing on that potential use of GPU?
It sure does, absolutely. I tend to include that with the other processors that we've already discussed, but yes, it's a great replacement for that as long as it requires two or more of the features that we're offering.
All right. Okay. Well, thank you again, Doug, for your time today. Just a reminder that today's session will be available here within the Military and Aerospace Electronics Tech Summit platform for the next 30 days. So on behalf of the Military and Aerospace Electronics Tech Summit and our sponsor, Coherent Logix, we would like to thank you for joining us today.